In today's lesson, we're going to be looking at combining trigonometric functions. All right, so your objective is that students will be able to prove the addition and subtraction formulas for sine, cosine, and tangent and use them to solve problems. So on our activator today, we took a look at a number of different functions and asked, are we able to just combine, if I looked at f of a plus b, could I just say that's the same as f of a plus f of b for lots of different types of equations? This does work for, say, linear functions, but what about for all the rest? Well, we'll take a look at that, but the big one that we're going to really focus on today is going to be the sinusoidal functions. Does that work for them? We're going to do an exploration. We're going to look at adding inputs and adding functions. We're going to develop an addition formula. We're going to develop a subtraction formula. And these are for our sinusoidal functions. And then we're going to look at some identities in calculus. All right? So that's what we're going to be doing in our lesson today. So let's swing back to that activator question. And this was the question here. We're looking at our linear function where we had f of x equals 3x. All right, if I said, okay, does f of a plus b, all right, and in this case, it's 3x. So does 3 times a plus b, is that the same as 3 times a plus 3 times b? And the answer is yes. Based on the distributive property, that's always going to work. All right, it works out there. But what about, say, for a quadratic function? Well, let's start out by saying, okay, well, let a equal 0 and let b equal 1. All right? If we plug those in, and I say, okay, f of 0 plus 1. All right? All right, f of 0 plus 1. Is that the same as, that's like saying f of 1, right? That equals 1 squared, which equals 1. Is that the same thing as saying f of 0 plus f of 1? Well, that would be 0 squared plus 1 squared equals 1. Hey, it checked out. It worked. All right, but it worked for those numbers. But would it work for everything? In the first example, when we looked at the linear, we used variables, so we could say that will work for everything. In this example, we just plugged in a couple numbers. Well, let's try another set of numbers. All right, what if I say let a equal 2 and b equal 3? All right, does 2 plus 3 squared, does that equal 2 squared plus 3 squared? That's the question. Well, 2 plus 3 squared is 5 squared, which gives me 25. Does that equal 4 plus 9? It does not. So for quadratics, it could work in theory if we had 0 and 1, but it doesn't work for everything. So we're unable to set that as a rule. We're unable to say f of a plus b equals f of a plus f of b. That does not hold true for quadratics. If we were to go ahead and for the radical do the same thing, let a equal 0, b equal 1, it would actually work out, right? The square root of 0 plus 1 equals the square root of 0 plus the square root of 1. That actually checks out. But if I use 2 and 3, does the square root of 2 plus 3 equal the square root of 2 plus the square root of 3? If you plug that into a calculator, you would end up getting the square root of 5, which is about 2.2. Does that equal square root of 2 plus square root of 3, which is 3.146? That does not work. So once again, for radicals, it works for some, does not work for all. All right, so we saw it works for linear, but you may be seeing a pattern that this does not actually work for everything. All right, for exponential, once again, it's going to work for some and not all. All right, and we could go through examples. If you want to see one where it works for both, let a equal 1 and b equal 1. All right, if you were to do that, you would get does 2 to the 1 plus 1, right? Is this the same as 2 to the first plus 2 to the first, right? Does 2 squared or 4 equal 4? Yes, it does. But any other numbers, it's not going to work. It's the same pattern. For logarithmic, we end up finding something very similar. We can make it work for some values. For example, if a and b are both 2, it works out. But for other numbers, if I had 1 and 2, it does not work. All right. But the one that we really want to focus on, all right, so once again, it's the same, right? Works for some, not all, is sinusoidal. Will it work for sine, for sinusoidal functions. Does f of a plus b equal f of a plus f of b? And the way in which we can think about this is, let's say, let a equal pi, let b equal pi over 2. And these are radians, okay? I'm always dealing in radians. So does f of 3 pi over 2, that's the sum of a and b, is that the same as, and for function here, this is sine. So instead of f, I should have written sine. So let me erase that. So does the sine of 3 pi over 2, does that equal the sine of pi plus the sine of pi over 2? Does that work out? Well, the sine of 3 pi over 2 is negative 1. The sine of pi is 0. The sine of pi over 2 is 1. So does negative 1 equal positive 1? It does not. So once again, we can't do this for sinusoidal functions. We can't just combine the functions. So we need an alternative. We need to do something different. So what do we need to do? All right. What we need to do to be able to find the, for example, sine of a plus b, or sine of, in this case, we write it as alpha and beta. If we want to find those values, there's a little bit of, we have to kind of think outside the box. And so we're going to start out by taking a look at these two diagrams. All right. Essentially, what we have here is we have a triangle that we've drawn with angle alpha. Oop, and that's way too large there. Let me fix that. Angle alpha right here, it's this inner angle, and beta is this smaller one. And I say, okay, I want to just take this and I want to represent the subtraction of those two angles. And the way in which we can do that is by just rotating our triangle to the right. So all we did is take this angle here, which is alpha minus beta, and we just rotated it to the right so we get this. Now, what we know from this is that these two triangles are the exact same. I know that these two triangles are identical to one another, meaning this distance between these 2 points is the exact same. And this becomes super important, all right? Because we're going to use the length of that segment, knowing that they're equal, to try and come up with a way to add and subtract sine and cosine. You might say, well, how does the length of that segment get us there? Well, the way in which it gets us there is because we know that when we're using a unit circle like this, that the x and y coordinates are based on cosine and sine, right? And so we have our coordinates of all of these points. We know what they are, and the length is going to be written in terms of sine and cosine. So we're going to be able to come up with a couple of equivalent expressions for that length that will help us to be able to add and subtract angles when dealing with sine and cosine. So let's just jump right ahead and look at how this is going to work. So we're going to be asked to calculate the length of segment AB. That's the one from the original image, which we have here on the screen. It's a little bit small, but it's there as a reminder. And if I say, okay, I want to find the distance between those 2 points, well, we can just use the distance formula. All right. And if we remember what the distance formula is, it is this. It's going to be the square root of, we're going to take our x value of each, and we're going to subtract them and square them. We're going to find the difference of the x's. So it's going to be cosine of alpha minus the cosine of beta squared plus, this is just using the Pythagorean theorem here. It's actually extremely helpful. It's just the distance formula that we've been using since Algebra 1. Sine of alpha minus sine beta squared. All right? So that's what we do there. Now, if we actually square these, multiply them out, and we're going to do this, and this is important, we end up with cosine squared alpha minus 2 cosine alpha cosine beta plus sine squared alpha minus 2 sine alpha sine beta plus sine squared beta. So it's a square root of all of that. All right, well, the nice thing is I have cosine squared alpha plus sine squared alpha. Well, that's just 1. We know that's just 1. I also have, let's see, I have that. Oh, and I left off. I missed a part here. I also had a plus cosine squared beta. And that cosine squared and sine squared, those add up to 1 as well. So I can simplify this to now I have 2, right? 2 minus, and I can factor out a 2 from these. So I'm going to factor out a 2 times, and I have cosine alpha, cosine beta, plus sine alpha, sine beta. And you might be like, whoa, this is just too much. All right, and we're going to end there. That's what we get for that distance. All right, great. How does that help us? Well, the way in which it's going to help us is when we look at the next piece, because now we're going to calculate the length of that segment, which is the same. These are congruent, right? But we're going to calculate it using our new points for our new angle once we've done the subtraction. So in this one, to get it, we're going to have square root. Once again, we're just using the distance formula. We have cosine of alpha minus beta minus 1 squared. Fortunately, because we have the 0.10, it actually is much, much cleaner. We have a lot less in here, plus the sine of alpha minus beta minus 0 squared. And then we can multiply this out. We end up with the square root of cosine squared alpha minus beta plus sine squared, or actually, I'm skipping ahead. I'm just simplifying before I get there, putting the cart before the horse. So we're actually minus 2 cosine of alpha minus beta plus 1 squared. That's everything from the left. Plus then, because of the 0, this becomes very simple. Sine squared alpha minus beta. All right, we have the cosine squared and the sine squared. That's just going to be 1. We have 1 squared. That's just going to be 1. So we're now left with the square root of 2 minus 2 cosine of alpha minus beta. Well, look at this. This answer looks very similar to this answer, 2 minus 2 times something. Well, notice, what do we have here? We have cosine alpha minus beta. So I know that cosine of alpha minus beta, or the subtraction of two angles, is going to equal this piece here, cos A cos B plus sine A sine B. Cosine A cosine B plus sine A sine B. All right, this is our formula for subtraction with cosine. So based on what we just did for determining how to find the cosine of two angles that we subtract, we're actually able to use that information. We can use the fact that cosine is even, so the negative cosine is equal to the same as cosine, and then we could use some of our identities like sine theta is the same as cosine of pi over 2 minus theta, etc. We can start like plugging in different values, and we can actually come up with, just based off that one example that we did, the following formulas. All right, so we learned that the cosine of a minus b, or alpha minus beta, is cosine alpha cosine beta plus sine alpha sine beta. Cosine of alpha plus beta is cosine alpha cosine beta minus sine alpha sine beta. Sine of alpha minus beta is sine alpha cosine beta minus cosine alpha sine beta. Sine alpha plus beta is sine alpha cosine beta plus cosine alpha sine beta. And I could just keep reading these and reading these. For tangent, you can see them here as well. But we can use these formulas now to answer questions about when we try to combine functions, or when we try and add angles or find the sine or cosine of two angles when added together, etc. These are additional identities that we now have to add to our toolbox when working with trig functions. So in this lesson, we explored the origins of the addition and subtraction formulas for trigonometric functions. In the next lesson, we're going to extend these understandings to solve problems using these formulas at the appropriate times. So you should be able to prove those addition and subtraction formulas and begin solving problems by using those formulas.